Hello, this is John Miares, and in this lesson, we're going to take a side trip to section 14.1, which is only available in the electronic version of this textbook. If you only have a hard copy, I can make available copies of this textbook section in PDF form, but don't expect that it's going to meet guidelines for accessibility because essentially it's just a scanned copy of the book pages. The topic comes from a branch of mathematics referred to as combinatorics, which, if you break down the roots of the word, com means to count, bin means two, and torix means twisted. So, one way of looking at this is we're talking about twisted ways of counting two or more things. Some semesters I lead off with this topic, and other semesters I don't. And if you look at the official syllabus for this course, this section is considered optional mostly because it doesn't exist in the hard copy of the textbook anymore. But I want to make sure to cover this section because A, I like teaching this section because combinatorics is the foundation for the study of probability and statistics, which, as you remember, I'm a professional statistician by trade. And B, it will make our understanding of section 12.6 that much easier. If you're worried about looking at a topic with a name so difficult to pronounce like combinatorics, let's just simplify this lesson by calling it what it is, the principles of counting, which sounds like something much simpler. When we go further than that, we'll begin this lesson by looking at a problem that most of us have to deal with every day, and that is figuring out what to wear. So here's our first problem. Suppose Xander, my son's name is Xander, has 10 different t shirts, 6 different pairs of pants, and 3 different pairs of shoes in his closet. How many possible outfits can Xander create if he must wear one t shirt, one pair of pants, and one pair of shoes from his closet? And we're going to ignore the boundaries of good taste. It isn't obvious from the outset what we're supposed to do with this information. So maybe we can pull out the numbers and write them down. We have t-shirts, we have pants, we have shoes, so we can fill in the slots like what you see here. We have 10 shirts, 6 pants, 3 pairs of shoes. So now what? The trick is that we need to consider all possible ways that these different items of clothing could be mixed or matched. One way we can visualize this is with a tree diagram. This diagram, for example, shows all the possible ways that one can match the 6 pairs of pants in Xander's closet with the 3 pairs of shoes he could possibly wear. With 6 different pairs of pants and 3 possible pairs of shoes to wear with each pair of pants, you can see that there are 18 total paths that one can have when starting at the top of this decision tree and working our way to the bottom. We have pants 1 and then shoes 1, 2, 3. Pants 2 could be worn with either shoes 1, 2, or 3, and so on. With that, it seems that the number of ways to mix and match the outfits would be to simply multiply by the number of pants and the number of shoes, which would give us 6 times 3, which is 18. Now let's throw the shirts in here for good measure. I couldn't construct a tree diagram like this big because 10 pairs of shirts on top of all of these other branches just was not going to fit very well on this slide. But if I have 10 t shirts and 6 pairs of pants and 3 pairs of shoes, you can probably imagine for each t shirt, you're going to have 10 different branches coming off of those little shoe branches at the bottom of this tree. So ultimately, we will want to multiply to get those results together to get 10 times 6 times 3, which will give you 180 unique outfits. Here is a similar example. From a restaurant menu with 6 possible appetizers, 12 main courses, and 4 different desserts, how many meals can be created consisting of 1 appetizer, 1 main course, and 1 dessert? The process is going to be very similar, but I'm not going to construct a tree diagram this time. nor in your homeworks would I ask you to do so either. The first thing I'm going to do is write down the three slots that represent the number of items I can choose from each group. We'll have a slot for apps, a slot for main courses, and a slot for desserts. I can choose one item from each group. So I have six possible appetizers. I can choose one of the 12 main courses, and we can choose one of the four dessert possibilities. Given those options, 6 times 12 gives us 72, times 4 multiplies out to 288 unique meal combinations. The formal terminology we're using here is referred to as the multiplication rule for counting, but in short, I like to call this the slot method. Here's the rule in math speak. Given a combined action or event, in which the first action can be formed n sub 1 different ways, the second action can be performed n2 ways, and so on, then the total number of ways in which the combined action can be performed is the product n sub 1 times n sub 2 times n sub 3 all the way up to n sub k, where k is the number of actions which must be performed. What this basically says is that if you're talking about mixing and matching ways of doing things, you can set up slots and fill them in with the number of ways of doing each thing, so long as these are independent events. Then multiply the numbers to get the results. Let's try another one. A password must consist of exactly 8 characters, which can be letters, not case sensitive, or digits 0 through 9. However, the first character cannot be a number. How many possible passwords can be created using this scheme? Now, just like before, I want to set up the slots and be ready to fill in the number of ways I can create a password. Each slot represents a character within the password. The first character cannot be a number, so given that there are 26 letters in the alphabet, we have 26 ways to fill that first slot. We're also told that the password letters are not case sensitive. If it made a difference, if we were talking about capital A versus lowercase a or capital M versus lowercase m, this number of options for that character would increase to 52. But let's keep it simple. In each of the other slots, we can have a character or a number, which increases the number of possible options to 36 when we include the 26 letters of the alphabet and the 10 digits going from 0 through 9. Each of the other slots is going to do the same thing. And just like before, we can multiply the results. But in doing so, we can save a little bit of time on our computation by writing all of those 36s as 36 to the 7th power times 26, which, if you work this through on your calculator, will give you scientific notation 2.0375 times 10 to the 12th power. Expand it out, this turns into 2,037,500,000,000 possible passwords, which sounds like a lot, but with hacking algorithms getting better, it's really not that many passwords. If we wanted to go more secure, we could make the letters be case sensitive, which, as I mentioned before, would double the number of letters needed or possible in each slot from 26 to 52. You could also force inclusion of a special character like an at sign or a pound sign or a dollar sign. And you might extend your password length to 12 characters instead of 8, which would make your password even stronger. Here's an interesting problem. In how many orders can the letters of the name Xander be scrambled? Well, when I'm talking about scrambling, I'm talking about doing this, where I'm rearranging the letters of the word Xander into another word like Randex or Andrex or Dexnar or something completely unpronounceable, or perhaps with the spelling that's a Canadian style, having an RE on the end instead of an ER. How many ways can this be done? Just like before, let's set up our slots. There are 6 letters in his name, and essentially we're saying that the first letter of the word can be any of the 6 letters given. So we'll fill our first slot with the number 6. The second letter, however, has to be something different than the letter already chosen. So let's say I've already chosen the letter R to be the first letter. There's only 5 letters available for that second slot. So I'll put a 5 in slot 2. Similarly, for the third slot, you're not allowed to use either of the first 2 letters you picked, so you only have 4 choices left. In a similar way, you can have one less choice for the fourth slot, one less choice for the fifth slot, and once the first 5 slots are filled, there's only one letter left that you haven't used to put in to the last slot. Multiplying all those together, 6 times 5 times 4 times 3 times 2 times 1 will give 720 possible choices. Let's try something similar. In a horse race with 8 participants, in how many orders can the 8 horses finish the race? Again, let's set up our slots, one for each place in the race. The winner of the horse race can be any of the 8 horses, so let's put an 8 in that first slot. Once the winner is picked, there's only 7 horses available to become the second place winner. And for the third place winner, only 6, and so on, and so on, and so on, until we get to the last horse, and there's only 1 horse left who can come in last place. Multiplying all these together will give us 40,320 possible orders that the horses can be rearranged. Now, some of you may have seen this kind of multiplication pattern before, where you're multiplying a number by every number that came before it down to the number 1. There is some symbolism for this, and it looks like this. Now, when we read it, we don't just look at this and say, 8. Instead, we look at this and read it as 8 factorial. Let's put a definition up here. For any whole number n, we will define n factorial as the product of that number n by every whole number less than n down to the number 1. So symbolically, this will look like n factorial equals n times n minus 1 times n minus 2 times every other whole number less than it going down to the number 1. Now, we do have a special exception here, and we've defined 0 factorial as being equal to 1. Now, why we have it set up that way will become apparent later in this section. Next example. In how many possible batting orders can 9 players be placed in a baseball lineup? Same process here. First, we'll set up our slots. Then we can have any of the 9 players bat first. Then there's 8 people left to bat second, and so on and so forth down the line until there's only one batter left at the very end. We multiply all these together to get 362,880 possible batting orders, which could also simply be written as 9 factorial. Let's twist this up a bit. What if the highest paid player on the team must bat fourth and the pitcher must bat last? We still have 9 slots to fill, but the options for filling them are a little more limited. The highest paid player bats fourth. So there's only one highest paid player. We'll put a 1 in that fourth slot. The pitcher always bats last. There's only one pitcher, which means there's only one option to fill that last slot. From there, how many people are left to be the leadoff batter? Well, if two people are already picked, there's only going to be seven left. Then for the second batter, there are six choices, then five for the third batter. We've already got the fourth spot filled, so there's four options for the fifth slot, three options for the second slot, then two, then only one for the eighth slot. This is going to simplify as 5,040 batting orders when we multiply it all together, or 7 factorial. Now, not every one of these problems involves multiplying numbers going all the way down to the number 1. Here is such an example. In a horse race with 8 participants, how many ways can 3 horses win, place, or show? This time we still have 3 horses, but we're only interested in the top 3 finishers. Winning means they got first place means they got second place, and show means they got into third place. It will start in a similar fashion in that there are only 8 possible winners of the race. Once the winner is chosen, only 7 horses are left for second place, and then we have 6 horses left for third places. When we multiply this together, that's just going to be 336 options, since we really don't care about what happens with the last 5 horses at all. How about we pause for a minute to have you try this one on your own? In a club with 22 members, all of whom are eligible to hold an office, how many possible ways can a president, vice president, treasurer, and secretary be selected for the club? Well, we have 22 members, but we only have 4 slots to fill. So that's going to give us 22 people who could be possibly chosen from to be the president. Then, after the president is chosen, there are 21 people left over who could possibly be vice president, 20 people left over to be treasurer, and 19 left over to be secretary. Multiplying this out gives 175,560 ways. Now, you're probably noticing a pattern here in that these problems start out looking like they're going to be factorial type problems, but they stop at a certain point because we have so many slots we can fill. And you're probably sensing that there must be a pattern to these. And there is. This kind of selection, where order matters, is called a permutation. The number of permutations of a set n objects taken k at a time, denoted npk, or with p with the parentheses n comma k, is given by this formula here: n times n minus 1 times n minus 2, all the way down to n minus the quantity k minus 1. Or it could simplify as n factorial over n minus k factorial. Connecting this to the slot method, what we're essentially saying is I have n objects I'm grabbing and k slots to fill. So we're going to fill them in with the number starting with the number n and decreasing by 1 every time until you fill all the slots. Let's look at this from a couple different ways. This expression, NP3, what we're basically saying is that if I have 9 things and I want to pick 3 of them, how many orders can I pick those 3 things in? Well, since we're picking 3, that means we have 3 slots to fill. So I can multiply 9 by 8 by 7, which gives 504. For something like 11p4, what we're saying is I have 11 things to choose from, and I want to pick 4 of them out and figure out how many possible orders I can pick those 4 out from. In this case, we'll have 4 slots and multiply 11 times 10 times 9 times 8 to get 7,920. I'll look more closely at that formula version with the factorial notation in on the next slide. On a basketball team with 12 members, how many ways can 5 people be selected so that each person is assigned a particular position? One point guard, a shooting guard, a power forward, a weak forward, and a center. Symbolically, what are we doing here? Well, we have 12 people on the team, and we need to pick 5 to go out and play on the court in specific roles, meaning it's going to matter who we pick to play point guard, who we pick to play center, and so on. Notation wise, it's going to look like 12p5. To compute this most easily, we can set up our 5 slots for the players and fill them in for the options we have, starting with 12 and then 11, 10, 9, and 8. When we multiply all those together, we get 95,040. If we wanted to apply that formula involving the factorials on the previous page, we said that npk would equal n factorial over n minus k factorial. Plugging in n equals 12 and k equals 5, that will give 12 factorial over 7 factorial, which we can look at in a few different ways. We can either expand out everything and then divide it out in order to get our answer, or we could look at the properties of what it means to be 12 factorial divided by 7 factorial. If I want to cancel some common factors here after expanding out the full product, we can see that everything from the number 7 going down to the number 1 in the numerator will cancel with everything in the denominator, giving us what we had when we were using the slot method: 12 times 11 times 10 times 9 times 8. What if order didn't matter when we were filling in the slots? Suppose we have a club with 22 members, but now we need to select a 4-member subcommittee to study a certain project. How many ways can those 4 people be selected? What makes this problem different is that the roles that the people are filling when they get selected for the group are not specific. It's not like we can have a president and a vice president and a secretary and a treasurer. In that case, it matters who's the president and the vice president. That switching places gives a different officer team. Here, we just have 4 people on a subcommittee working together to study a certain project. In that case, we could have a group like John, Paul, George, and Ringo, but that would be the same group as Ringo, John, George, and Paul, or George, Paul, Ringo, and John. So not only do we have to figure out how many ways to fill the slots, we need to consider how many ways these people can be rotated among each other and discount them somehow because they're simply a repeat of a previously selected group. Step 1. We still need to set up and fill slots like we did before. We have 4 people that we are choosing to be on this committee, so we're going to have 4 slots. 22 members are available to fill the first slot, then 21, then 20, then 19. So it starts out looking the same as there were 175,560 ways in which those slots could be filled. The next step is to figure out how many ways those 4 people can be selected and then be switched among each other to still be the same group. For that, we're going to set up 4 new slots. The first slot can be any of the 4 people that have already been selected. The second can be any of the 3 left over. Then the third can be one of the 2. And there's only one person left to be last. That means there are 24 ways or 4 factorial ways that those 4 people can shuffle up amongst each other and still represent the same group of 4 people. Now, how do we discount for those repeats? Well, what we're saying is that for every one of the possible groups of 4 that could be selected in step 1, there are 23 other identical ways that the same group could be picked, but in a different order. So we're going to divide the results. We'll take the answer from step 1, the 175,560 ways that the people could fill the slots to begin with, and then divide that by 24 to get 7,315. This is the number of unique groups of 4 people that can be chosen from the group of 22 to form this subcommittee, knowing that there are no specific roles on this subcommittee. Here's a similar problem, and it's a slight variation on the basketball team problem we looked at before. On a basketball team with 12 members, how many ways can 5 people be selected to play at one time, assuming it doesn't matter who plays in what position? The difference between this example and the one we did a few slides ago is that it doesn't matter who's playing what position. It's a total free for all, a pickup game, just 5 people playing to play. So we'll start by filling the 5 slots just like we did before. And we'll start by picking one of the 12 to be the first person on the court. Then we'll see there's 11 people left, and then 10, then 9, then 8. Multiplying these all together still gives the 95,040 we had before. Now, knowing that the positions that each person is playing doesn't really matter, we want to see how many ways we can rotate those 5 people among each other and still have the same group on the court. So we'll set up the 5 slots. We're going to take 5, the first person of the group of 5, then 4 times 3 times 2, and then times 1. Multiplying all that out gives 5 factorial, or 120 ways that those 5 players can shuffle up among each other and still be the same group of people playing on the court at that time. Finally, we're going to divide the results, which gives us a total of 792 possible groups of 5 that can be chosen from the original group of 12, knowing that the order they're being selected doesn't matter. This kind of selection, where order does not matter, is called a combination. The number of combinations of a set of n objects taken k at a time is denoted here with this lowercase n, then capital C and k, or C in parentheses n comma k, or you'll also see with an n over k looking like a fraction but without a fraction bar inside parentheses, is given by n times n minus 1 times n minus 2 all the way down to n minus k minus 1, which is our permutations formula, divided by k factorial. These can be further simplified by looking at this as n factorial divided by the quantity n minus k factorial, or k factorial, or more simply, the permutation formula npk over k factorial. Now, just so you know, these can be computed on the calculator. To get the combinations and permutations button, you want to press the math button, then use the arrows to get to the prob menu like so. On the TI-83, it'll say PRB instead of prob. Option 2 will give you permutations, NPR, and the combinations can be found under option 3, NCR. Now, this looks intimidating, all this symbolism, but it's really not. Suppose I want to connect this back to the slot method. You have k slots, you're filling them with numbers starting from the number n, then decreasing by 1 every time until you fill all the slots. After that, If you're confident that the roles for each slot are not going to be specific, then you want to divide by the number of slots factorial. That's what we have here. More simply, you can take the number of permutations and just divide by the number of slots factorial. Let's look at a few of these. If I wanted to calculate 9C3, which would be from a group of 9 things, choosing 3 for something where the order doesn't matter, we can multiply it out by using the slots to get 9 times 8 times 7, and then divide by 3 times 2 times 1, which will be 504 divided by 6, which is 84. You can also compute this as 9 factorial over 6 factorial and 3 factorial to get the same result. To do 11C4, let's say you have 4 slots to fill now in your numerator to get 11 times 10 times 9 times 8, then divide it by 4 times 3 times 2 times 1 to rotate the 4 things among each other. Then divide the results as 7,920 by 24, and you'll get 330. This can also be computed by taking 11 factorial over 7 factorial and 4 factorial. We show here how it looks on the graphing calculator when you type in these expressions taken from the math prob options. Now, the formulas are pretty straightforward to work with, and the calculator makes doing the computations foolproof. The hard part is in looking at a problem and trying to decide whether or not you're going to use combinations or permutations. Let's say the problem is given like this. In a raffle with 120 entrants, how many ways can a first prize, second prize, third prize, and fourth prize be selected? Is this a permutation situation or a combination situation? Well, there's a first prize, second prize, third prize, and fourth prize, suggesting that there are different prizes and it's going to matter who gets each prize. This is going to be an example of a permutation. Symbolically, we can write this as 120p4. Out of the 120 people, we're going to pick 4 to get our prize. And the order is going to matter because the prizes are specific. Computing permutations is just a matter of filling in slots, so I can take 120 times 119 times 118 times 117, and we'll multiply this out. We'll get 197,149,680. Now, changing the problem a little bit. Suppose now we have a raffle with 120 entrants. How many ways can 4 $50 gift certificates be awarded? In this case, since everyone is getting a $50 gift certificate, the order in which those gift certificates are handed out doesn't matter. So we can look at this as a combinations problem, and we'll write this out as 120C4. Of the 120 people, I want to choose 4 to get a gift certificate, and the order in which I assign them doesn't matter. Computing these by hand, we can start the same way we did with permutations, 120 times 119 times 118 times 117, but then we'll divide by the number of ways that the 4 winners of these gift certificates can be shuffled amongst each other, which is 4 factorial, 4 times 3 times 2 times 1. So that's now going to be 8,214,570 ways. What about this one? A restaurant offers 10 possible toppings for their pizza. How many ways can one order a 3 topping pizza? Let's pause for a second to think about this one. Is this a permutation or a combination? Does the order matter? Are the toppings specific? This one's a little bit deceiving because you're thinking in the back of your mind the toppings are going to be specific. It's going to say, well, I want to have pepperoni, I want to have sausage, I want to have mushrooms. But the key is this: once you put those toppings on the pizza, the order won't actually matter because they're all going to be mixed up anyway. So unless you're doing something funny and layering with the pizza where you're only going to put the mushrooms in the middle and then have a ring of sausage and then surround that by a ring of pepperoni, the order isn't going to matter. If they're all mixed up, a pepperoni sausage and mushroom pizza will be the same as a mushroom sausage and pepperoni pizza and the same as a sausage mushroom and pepperoni pizza. So this is going to be a combination problem. We have 10 toppings to choose from. We can choose any three, and the order in which they're put on the pizza doesn't matter. So we're going to start with 10 times 9 times 8 ways to fill the topping choices, and then 3 times 2 times 1 in the denominator to shuffle the toppings among each other. And then we can multiply things out to get 720 divided by 6 and get 120 unique three topping pizzas. Now let's change the problem up a bit. What if you were asked how many ways one can order up to a three topping pizza at that same restaurant? What that translates to is that we might have three toppings, but we could have fewer, maybe two, maybe one, maybe zero, which would be a plain cheese pizza. So let's see how we would compute those options. We've already calculated the number of three topping pizzas as 10C3. For the two topping pizzas, we're starting with 10 toppings and choosing two, or 10C2. For one topping, it's going to be 10C1, and for zero toppings, it's going to be 10C0. These will compute if we use our calculator or do our calculations longhand as 120 possible three topping pizzas, 45 possible two topping pizzas, 10 possible one topping pizzas, and then one plain pizza. Now, you might be wondering, you say 10C0, and usually you think zero, stuff with zeros usually collapses to zero. But if you think about it, you've got 10 possible toppings for your pizza. How many ways can you choose none of them? That would be one. You can say, I don't want anything on my pizza, and that is one choice. Remember when I said earlier that 0 factorial equals 1? This is the scenario where that becomes an issue because otherwise the formula has a 0 factorial in the denominator. So in order to do that calculation properly, we have to define 0 factorial as equal to 1. Similarly, for the one topping pizza, you have 10 possible toppings and you're only choosing one. So you're basically just saying, I can have one of these 10 pizzas. For the two topping pizzas, you have 10 times 9 for the two slots in the numerator divided by 2 times 1, which is 2. 90 divided by 2 gives you 45. So I want to find all the ways that I can have up to three toppings, and I can see the list of all the three topping, two topping, one topping, and zero topping pizzas. What are we supposed to do with these? Well, we're going to add them all together, and that total is going to click to be 176 possible pizzas. How do we decide whether to add or multiply in cases like this? We need to look at the keywords implied in this problem. If the keyword is or, I want to do this, or I want to do this, or I want to do this. I want to have a three topping pizza, or a two topping pizza, or a one topping pizza. We will want to add those numbers separately to get the total. Whereas if I want to do this and this and this, I need to wear a shirt and a pair of pants and a pair of shoes. I want to multiply out the possible ways to get things done. So or means add and means multiply. What if order only partly mattered? Let's look at a slightly different problem. How many ways can the letters of the word Lansing be rearranged? This one is a little bit different than the one where we were rearranging the letters of the word Sander because the word Lansing has two N's in it. So we have to figure out how that is going to impact this problem. We're going to start the same way as we did before by filling the slots. There are 7 slots, 7 letters. So we're going to have 7 times 6 times 5 times 4 times 3 times 2 times 1, or 7 factorial ways that we can fill the slots to begin with. This multiplies out to 5,040 possible rearrangements of those 7 letters. Now let's look for the repeats. There's 2 N's in the word Lansing, and they can be scrambled up 2 ways, or more specifically, 2 factorial ways. To demonstrate this, if I was to make one of the N's red and the other one blue, we can see that if I swap one for the other in one of the rearrangements, like this one I'm showing here that looks like nin lags, the idea is that the 2 N's could swap places and I would still have the word ninlags here. So what we're going to do is divide the 7 factorial ways to fill the slots by the 2 factorial ways that those 2 N's can be flipped amongst each other, and that will give me an answer of 2,520. Let's try a few other problems like this. The word college also has 7 letters, but this time it has 2 L's and 2 E's. So we want to start by filling in the slots, then dividing out by the number of repeats, factorial. In this case, we start with 7 factorial for the 7 letters in the word college, then we divide by 2 factorial for the 2 L's, and 2 factorial again for the 2 E's, which gives us 1,260 unique words that I can scramble the letters of the word college into. Let's try something bigger. How about the word Kalamazoo? Kalamazoo has 9 letters, which includes 3 A's and 2 O's. So what we'll do this time is I want to start with 9 factorial to account for the 9 letters that I have. Then I will divide it by 3 factorial to account for the ways that the 3 A's can scramble among each other, and by 2 factorial to figure out how the 2 O's are going to scramble amongst each other. That will reduce to 30,240 possible rearrangements. Now, here's one that I bet some of you were already thinking about in the back of your mind. How many ways can we rearrange the letters of the word Mississippi? Why don't you go ahead and try that one on your own? I'll pause the video and then we can come back in a couple minutes to see how we did. So here we now have 11 letters. We have in those 11 letters, there are 4 I's, 4 S's, and 2 P's. So we're going to start then by taking 11 factorial for the 11 letters in the word Mississippi. We'll divide by 4 factorial to account for the 4 I's. We'll divide by 4 factorial again to account for the 4 S's, and divide by 2 factorial for the 2 P's. That will give us a total of 34,650. I don't need to worry so much about the letter M because it's not repeated. If you wanted to account for it, you could divide by 1 factorial for the one letter M that's there, but that's not necessary since 1 factorial is 1. The other thing I will warn you to keep in mind is that you probably should have parentheses around your denominators when dividing out the different terms on your calculator. Otherwise, your calculator might not process the computation with the right order of operations. The problems that we just did, we call permutations with repetition, and they are kind of in between a combination and a permutation when it comes to actual counting. Remember, in permutations, order matters for all the slots because the roles in each slot are specific. In a combination, none of the roles are specific, so the order doesn't matter in how the slots are filled. In permutations with repetition, the order of the slots matters for the most part, except for the repeated values. So the technical definition involving permutations with repetition is given here. For a set of n objects in which n1 are of one kind and n2 are of another kind and n sub k are of a kth kind, the number of distinguishable permutations, again, we're talking about unique rearrangements of those letters, is given by n factorial divided by n1 factorial, n2 factorial, n3 factorial, all the way up to nk factorial, where those values in the denominator represent the slides and the slots that are repeated. Here's a similar problem that doesn't involve specifically rearranging letters in a word, but does involve permutations with repetition. A boat has 3 red, 3 blue, and 2 yellow flags with which to signal other boats. All 8 flags are flown in various sequences to denote different messages. How many such sequences are possible? The strategy here is we're going to think of the sequence of flags as an 8-letter word that consists of R's for the red flags, B's for the blue flags, and Y's for the yellow flags. One such sequence might be RB, RB, YB, RY. Another might just be simply BBB, RRR, YY, while a third could be YB, RRB, YRB. When we look at it like this, it has become a word with 8 letters in it that has 3 B's, 3 R's, and 2 Y's. It doesn't really matter that that word is not something pronounceable in the English language, but I can still treat it like the way we were unscrambling the letters of the word Mississippi. We have 8 different letters, so that's going to give us 8 factorial in the numerator. Then we can divide by 3 factorial for the 3 B's, 3 factorial for the 3 R's, and 2 factorial for the 2 Y's, and that will reduce to 560 possible orders. I've got one more type of combinatorics problem that I'd like to introduce before we close this out. Suppose 8 people are chosen for a dinner party. In how many possible orders can those 8 people be A, standing in a line from left to right, or B, sitting around a circular table with no head to the table? The strategy for part A is no different from what we've done before. There's 8 people, 8 places they can stand, the order matters, so it's just going to be 8 factorial, or 40,320. Now, in part B, this gets a little bit trickier because you're first thinking, well, there's 8 chairs sitting around the table, 8 people filling them. What's the difference? Well, it has to do with the fact that there's no head to the table. So let's say this is a picture of a dinner party where we have 8 people, where you can see a Dan at the top, followed by Fran, Cam, then Ann, Ted, Sue, Mel, and Val, going all the way around in clockwise order. We're assuming that there is no head to this table. So what that means here is that everyone moves one chair to the left. Let's say Dan was sitting where Fran was sitting, and then Fran moves to where Cam is sitting, and so on. They would all be in different chairs, but they'd still be sitting in the same order. The same thing would happen if everyone moved two chairs to the left, or three chairs to the left, or all the way to seven possible rotations from their initial spot. In fact, if you include the first method, there are 8 possible ways that this particular group of people can be sitting around a table, possibly in different chairs, but still in the same order. So what we'll have to do is divide 8 factorial by 8, which actually simplifies to 7 factorial, or 5040. We call situations like this circular permutations, and to compute the number of ways to arrange n distinct objects around a fixed circle is given by this formula. N factorial represents the number of slots or seats to fill. Then we can divide by n, which represents the number of ways that people can rotate seats to the left or right and still be in the same order. Here's one more example of this. In how many ways can we order 12 coats if they are hung on a straight rack or hung on a circular rack? For part A, we can just use the slot method as we've done all along. 12 times 9 times 8 times 7 all the way down to 1 will be 12 factorial, or 479,001,600 orders. For part B, we take the 12 factorial number of ways to put them on the rack and then divide by 12 to account for the number of ways they can be rotated on the circular rack. And we get 12 factorial divided by 12, which happens to also be 11 factorial, to get 39,916,800. Okay, we've come to the end of yet another lecture. Here's the problem challenge problems. If you don't have a copy of the ebook, I will make sure a copy of the section 14.1 textbook problems are available in this week's D2L content folder. Summing up, what I can say is that when it comes down to it, you're looking at how many ways that slots can get filled, and most often multiplying the results, because you're saying, I need to pick a president and a vice president and a treasurer, and the word and is going to mean multiply. On occasion, you're trying to figure out a way to do one thing or another thing, and the keyword or means we'll want to add. If the order of selection matters, the roles are specific, you're using a permutation formula, just filling slots. If the order doesn't matter, the roles are not specific, then you need to divide out by the number of ways they can rotate among each other, which is a combination. You have buttons on your calculator to evaluate these, so you don't have to do them all by hand, but you will need to be able to read into the problem to distinguish, is this a permutation problem or is this a combination problem? There's a few that are also permutation with repetition, like unscrambling the word Mississippi, and a few with circular permutations, like we just did. They're not hard, but there is a lot to keep up with. Give these a try, and if you have any questions, please post them on the discussion board or send me an email, and we can be sure to get your questions answered. Thanks for watching, and we'll see you all soon.